Well, good morning again, team. Chemistry coach coming at you. We're looking at some lab stuff today, qualitative observations. You usually spend the first few weeks, if not month or so, in general chemistry laboratories learning how to do quantitative observations, aka measurements, right? And we taught you, you look at the absolute uncertainty video, how to make measurements, right? How can you be a good scientist in general, not just a chemist, if you don't know how to measure things properly, right? So we're always measuring masses and volumes and temperatures and yada, yada, yada. But there are always times where there's no measurement involved. We're just going to study something qualitatively, right? Mix chemical A with chemical B. We're trying to see if a chemical reaction happened, trying to see maybe if there's some kind of patterns going on. There's always some good periodic trend type experiments where you're looking for color changes and whatnot to indicate patterns. Chemistry is a lot about patterns. So we want to learn how to be chemical detectives, right? We want to be able to record a tremendous amount of data without missing. Sometimes it's a fine little detail that's the smoking gun to make some conclusion about some kind of change that's occurred. And if you're sloppy with your recording of your qualitative observations, you might miss it and make the wrong conclusion, right? So we got to go full CSI here, get every little detail, right, and take a look at it and see what we can deduce from it. So again, this is experimental data that does not include units or some kind of numerical value, right? So mostly colors, phases, etc., etc. So I would highly recommend you review the video for signs of a chemical reaction, right? From just I forget what chapter section that was, but easy to find. Probably looking at starting chemical reactions because those are chemical changes, and look through the signs of a chemical reaction, including color change, formation of a solid, formation of a gas, and a change in energy. Now, change in energy is not always noticeable. Sometimes it's just one of these, sometimes it's more than one. But what I'm going to do is look at each of these in turn and correspond it to what we're looking for in lab. Right? What would make us conclude there was energy change? What would make us conclude there was formation of a gas, indicating a chemical reaction had occurred? Sometimes you can't really see a solid form. You have to look in a slightly different way at the clarity of a particular mixture. Color changes are pretty obvious, though. That's why we list that first. And the clarification for formation of a solid or a gas, that can include a phase change. That's a physical change. That's not a chemical change. So, I could have liquid water and vaporize it. Well, that's not a chemical change, right? I could take water and freeze it into an ice cube. I am forming a solid. That's not a chemical change. So this does not include phase changes. It's usually upon mixing two or more chemicals, like formation of a solid. Usually you're mixing two or more solutions to form a precipitate or something like that. Pretty limited at home here with what I can do, but we'll try to do a few demos. I got my trusty goggles on. All right, so let's talk about each one in turn. The data we're looking for, and then once we're done with that, we'll organize it. I have a qualitative observation handout on my website that you can print out and take with you to lab and just kind of follow it step by step. Right, this is a part of it here, so it's just kind of step A, step B, step C, what you're looking for each particular solution or whatever your reactants are. But let's look at these in turn and correspond it to what you're looking for in lab. Let's start with the easy one first, color change. Now remember, when you're recording data, you've got your reactants. Well, you hopefully got at least two. I guess you could have one if it's a decomposition reaction, but most likely you're going to have two, maybe more. But in general chemistry labs, typically two. And then you're going to mix them together, shaky, 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 and form a product, right? That product obviously is going to be a mixture. Now your reactants could be mixtures, solutions, or whatever, or they could be pure substances. Might be an element or a pure compound or something. Doesn't really matter. If you're looking for, the key is color change. You can't just say it turned green. What's it? Right? Was it green to start with? It's not enough data. So you have to give the colors of each individual reactant first, all of them. What's the color of this one? What's the color of this one? Reactant one, reactant two. Mix them together and then describe the color of the final product, that mixture. Because we're looking for a color change. So if you have something pink and something blue, right, and you form something that's white, or if you have something colorless, remember colorless, clear means you can see through it. Colorless means it lacks color, right? So colorless would be a lot of things, a lot of acids and stuff, right? You can't really see the bottom. You see that doesn't have a color to it, right? This is hydrochloric acid, right? So that's a colorless solution. There's no color to it. If you mix two colorless solutions and you get something that's purple or brown or black, well, hello, that must have been some kind of change in the atomic arrangements, creating a new substance. That's a chemical change. Now, it can be kind of silly, but I've seen it happen in undergraduate laboratories. Be as specific as possible, right? If it's blue, try to get a specific shade of blue. Green, you can be a little more creative. Don't be weird, though, right? Try not to give, I don't mind in my labs if you want to have some fun, but if you're publishing a paper, I would probably pick a color that most people know. I wouldn't use something like sepia, because, a good chunk of people go, what the doo-doo is sepia, or chartreuse? I'm like, chartreuse, weren't they arguing about like the color of some royalty in England? That's a lie. No, it's chartreuse. No, it's yellow-green. Oh my God. Just give it a color that most people are aware of, right? Mauve. It's mauve. What's mauve? It's not like a purple shade of purple. It's like, so have fun in my class, right? But if you're publishing something, right, or doing a more, a higher level chemistry laboratory, try to be a little more, pick something that most people know. Another thing is don't pick vague colors. I see this is a little more serious, than ones that are more rare. But, I've had people put urine colored. I'm like, urine can be colorless. It can be yellow. It can even be red. If it is, go to the hospital fast, right? So it's depending who you're talking to, they may see it differently than you. Or cloudy. My absolute least favorite word undergraduate chemistry students use to describe something is cloudy. What does that even mean? Right? I can look out, Southern California, there's no clouds, but I can look at clouds. They can be white, they can be gray, they can be black, right? I spent 10 years in Minnesota. That looks like it's going to be a tornado. Run! Clouds can be many different colors. Some clouds are kind of wispy and you can see through. Some are real thick cumulonimbus clouds. I don't know if that's the name, cirrus clouds. I'm not a big meteorological person, but avoid weird things like that. See what I'm saying? That's vague, where people might not get the right. You have to get something that's specific. Get it? Get it? Okay. For each reactant and the product. Let's look at solid formation. You're ready for solid formation. This can get a little bit more confusing for people, nowhere near as easy as color change. A lot of times when there's a solid formation, there's a corresponding change in color, because a lot of times you're forming a precipitate upon mixing two solutions, right? If I mix a couple solutions, boop, you can possibly get a different colored solid. Hey. So anyway, sometimes if you're form a solid, it's pretty obvious. But I find in undergraduate laboratories, the majority of the time, you don't actually see the solid form, because the particles it forms are so tiny, like the precipitate particles, it's hard to see with your eye. And when you first mix them, you can't really see the particles. A lot of times you have to, say you mix them, you form this mixture, you got to kind of tilt it a little bit and get a little sliver of it and look into the light, and you're like, oh, there's a whole ton of little itty bitty tiny particles in there. So initially you don't commonly see the solid, but you notice there's a result of that solid forming. It's a change in light passage through, whatever that product is, that mixture, right? Light hits it. Does light get through? Some light get through or no light get through. That's called clarity. So we need to record the clarity for the initial reactants and the products. We'll look for a clarity change. So look for clarity change. So just like we're looking for color changes, when you're looking for a change, you need the initial colors and final colors. When you're looking for a clarity change, you would have to describe, if I mix these two, I'd have to describe the clarity of this one. How well can I see through it? What's the clarity of this one? How well can I see through it? Mix them together into a test tube or whatever. How well can I see through that, right? Is light getting through? Now, what we're looking for clarity is one of three answers. Clear, opaque, or translucent, right? So clear means all light passes through. Like I'm looking through this window right now. I can see fine details through it. All light's getting through. That's perfectly clear. Anything perfectly clear, we're going to call that a homogeneous mixture. It looks the same throughout, aka a solution. So anytime you form a product that's clear, we're going to call that product a solution. I guess you could call it a homogeneous mixture, but we'll just call that a solution because it's easier. It's less painful on your hand muscles. Now, if it completely blocks light, there's so many particles in there, light can't get through. You can't see through. It's like, I can't see you anymore. My hand is blocking all of the light. This calculator is blocking all of the light. I can't see anymore. Bloop. Right? That's called opaque. It's like trying to look through a door. Doesn't happen. All right. Translucent means that's partial light blockage. You ever go to somebody's door and they got a little window cut out around it, but it's this weird kind of milky glass or stained glass or something, and you look through, you ring the doorbell or whatever, and you see some image of a body coming at you, some ghostly image. You don't know who it is. It could be your friend or your mom, their mom or their sister. You don't know who it is. You know there's a person, but you don't know who it is, so you can't see fine detail. If it was opaque, you can't see anybody. You can't see through the door, right? If it was clear, you can know who that person is, right? It's the same detail here. If I mix a couple things together and I can perfectly see fine details through it, I can see like my fingerprint on the other side, I call that clear. If I can't see my finger at all, or maybe a pen or something, sometimes I'll take a pen, right? Of course, you're recording your qualitative data in pen. I'll take my pen, put it behind it and go, well, okay, I can see the color and the fine detail, so that'd be clear. If I can't see the pen at all, that'd be opaque. If I can see an image of a pen, sort of, but I can't see fine detail, I would call that translucent. Now, if you have translucent, where'd I put my black pen? I'm sitting on it. If you see anything that blocks light completely or partially, so if you form a product that's opaque or translucent, that's not the same throughout. So that's a heterogeneous mixture. So we'll call these just a mixture, right? At least in my classroom, if your product is opaque or translucent, we're going to just call that a mixture. That'll be our noun. And if it's clear, we'll call it a solution. Got it good? Let's move on to gas formation. Right, for gas changes, right, or not gas change, gas formation, a couple things you're looking for. The most obvious would be bubbles, right? I mix a couple, maybe I put a solid in with a liquid and I start seeing bubbling, bubbling, bubbling. Well, that's pretty obvious, right? Or two solutions, I see lots of bubbling. And it's bubbling kind of, you'll see a continuous rate. It may end, right, within a few seconds or a minute, because once the reaction's over, the bubbles stop and they just dissipate. So you gotta notate bubble formation pretty quick. Right? So if you don't see bubbles, you don't need to write that. Only write it if you see them. So you don't have to say no bubbles were visible. That's obvious if you don't write it. And it's the official term is effervescence, but I hardly see anybody. It sounds too much like a rock group that I like. Went to see them in concert too. Yay! Great music. But be careful, because if I say I have say a milliliter of a solution here and a milliliter solution here, and I mix them, and the air pocket between them collapses, so you might see a bubble or two due to the air pocket collapsing, and then just goes away real fast. That's not gas formation. That's just the air pocket collapsing. So don't use that as a sign of a gas. You would actually, once you mix them together, shake it, right? Make sure you shake it. And if you see constant bubbling coming on for a limited period of time, think like champagne bottles or something like that, or you're pouring soda pop, you see all those bubbles come. That would be the indication that you formed a gas. But some gases, there are no visible bubbles. No, but you can look for an odor change, right? It smells like this to start with, smells different to end with, right? Maybe both your reactants were odorless, and then it smells like a lemon, or a skunk, or a rotting fish, or a bad burrito day, if you know what I mean, stuck in the car on a drive to Vegas with your friends. All right, anyway, dissipation of gas. So we need to record the odor of all reactants and the product. You're looking for odor changes. You just can't say smells like lemons. Well, what did it smell like to start with? What were the original reactants? You got to be complete in your data. Also, be as specific as possible. Don't just say, it smells. Well, it doesn't tell me diddly jack squat. The odor change. That doesn't tell me diddly jack squat. the odor changed is a conclusion. What made you indicate that, right? All right, so here we go. So obviously if it has no odor, call it odorless. If it does, try to be specific. Smells like, vinegar. Acetic acid has that typical smell. Or like I said, skunk or something cat litter box, or smells like somebody's getting a permanent or something. A lot of times, especially when you're in first semester of general chemistry, there'll be smells you're not familiar with. It's like, I don't know, I never smelled that before. So here's a couple terms that are, I guess, acceptable. Acrid is like a sharp, biting, unpleasant odor. You're like, now remember, when you're smelling things, don't be like, oh, right, waft it towards your mouth, towards your nose. If you don't smell anything, you can move it a little bit closer. And if it's like, ooh, makes your eye water a little bit, you're like, oh, that hurt, man, that was unpleasant. You get this biting, sharp odor, usually not very good. Commonly with acids and stuff. We can call that acrid. I'm okay with that. This generic, unpleasant, biting, sharp odor. Pungent's a pretty common one. It's an unidentifiable one. You don't know what it is, but it's bad. It smells horrible. You're like, oh, wow, that was nasty, right? So pungent's an okay one for that. But ideally, if you can, give it a specific smell that people can relate to. All right, let's do our last one, energy changes. That's the fun one. For energy changes, there's three different types you may run into. The most common by far is a temperature change. You would never say, we don't put conclusions in our observations, just what we see and we make conclusions from it. So you'd never say, saw an energy change. Well, you can't see an energy change. What made you conclude there was an energy change? Well, a temperature change. So you need the temperatures of all your reactants and the product you form. Now, in second semester general chemistry for thermodynamic stuff, we're going to measure temperatures with a thermometer. But very commonly, we're not going to measure. We just want to know if the temperature changed, so we don't need a specific value. Typically, they start at room temperature. If you haven't done anything, they just start at room temperature. So we can just say room temperature, or RT if you want to use an abbreviation. And then you can feel it, and you got to do it pretty quick. When you mix it, you want to detect an odor, and then feel, because that temperature change can be pretty quick. So after you shake it, feel, does it get warmer than room temperature or colder than room temperature or stay at room temperature? You want to note that, all right? Because if it changes, if it's noticeably colder or warmer, that's an indication you had a chemical reaction. Hey, right? Don't ever say it was exothermic or endothermic. That's a conclusion, my friends. Ha 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 ha, no conclusions in your observations. Light formation is a fun one. Yesterday was the 4th of July. I walked out in the street. I could see from where I'm at. I'm up higher. I can see all of Norco and Ontario. I took my kids out there, and it just lights everywhere of different colors. It was awesome. And we had some sparklers. The kids are running around. Wee! And land, we just take a strip of magnesium, light it up on top of it. Oh, yay! Right? Sometimes you're like, that hurt my eyeballs. Well, that's an indicator that there was an energy change and thus a chemical reaction. My favorite, flame. Blown myself up in some flame a few times. Pretty big indicator there was a pretty major chemical reaction going on with a lot of energy released, very highly exothermic. And it hurt. So we try to avoid the flame formation in undergraduate laboratories. We have a few labs where we'll take little tiny chunks of sodium or potassium, put them in water. Psst, oh, yay! Especially with potassium, little lavender flame. So it's all kind of fun. These are usually pretty obvious and easy to do. All right, let's organize this. This will be different whatever professor you have. But for my class, we're going to use the qualitative observation handout. So print that from my website. And we're going to organize all of the information. Remember, we're looking for color changes, clarity changes, odor changes, and we're going to organize them in a specific order. Now, it's correct as long as you get all the data, but I'm going to try to train you to do it in the same way each time so that it becomes routine in your brain. Here we go. Couple tips here. Generically, when we're doing qualitative observations, we'll do the specific order on the next board. Obviously, follow the qualitative observation handout that I have. Now, if you're in a different class, use whatever their tips are, right? Whoever's giving you the points, follow what they're doing, right? But if I'm the captain of the ship, this is what I'm a stickler on proper details. I'm preparing you for success out in the real world. So I'm not going to shortcut anything in lab. I want you to be the best you can possibly be, the best you can be. So here's some tips. Avoid making conclusions. I've already stated this. No conclusions in the observations. Observations are what you see. We will conclude what that meant later, right? So you'd never say no reaction occurred. How do you know? There might have been something that happened that you couldn't detect. I would never say no precipitate formed. How do you know? Maybe there's some particles that are so small they don't even block light partially, right? Like called colloidal precipitates, right? So be very careful. Don't ever say a reaction occurred. That's a conclusion from the data. Oh, see, you would never include the identity of any products you think formed. That would be a conclusion, right? You might think it's lead 2 sulfide, but you can't say that, all right? Your reactants you could, because it's on the reagent bottle, but for products you can't make conclusions in the observations. Good. Biggest mistake I see people make. Avoid referencing yourself. Not the end of the world in undergraduate lab, but try to get away from I saw or we did or we mixed or I, that kind of. Try to keep it very generic, right? Very scientific, right? So keep away from that kind of verbiage. Use complete sentences, of course, proper grammar, proper spelling. Watch all that stuff. Write it as if you were publishing a paper. You would never have, if your grammar was wrong, your spelling was off, or you were choppy in your sentences and you tried to get that published, they'd laugh at you. So practice the right way now. Don't rush it, man. Don't half-butt, what you're learning in lab. In my class, use pen for all primary data. So any kind of observation, quantitative or qualitative, they count as primary data in pen. Now conclusions, that's secondary data. We could do that in pencil, right? Because they're a lot of commonly wrong. Include all required details, right? Looking for the 4 signs of a chemical reaction, all the odor changes, clarity changes, color changes, initial and final temperatures, all of this stuff. It's a lot we have to write. So we're going to want some abbreviations just to make our lives less miserable, all right? So let's look at the qualitative observation handout and how we organize the data that we're going to be recording. Here we go. Here's our order. I think it's intuitively obvious. You start with your reactants. Why would you describe your products when they come after you mix your reactants? Don't try to form everything and then go back and think about what were my reactants. If I've got 2 different reactants, record reactant A, record reactant B separately before you mix them. Don't go back and go, what color was that? Oh, I forgot what odor that was. Here we go. Now here's what I want you to look for. Now, again, as long as you've got this data, that's good. But in my class, in lab, I'm going to get you, I read all your observations. I want you to do it in this specific order because that allows you to use specific abbreviations. You can go faster. Plus, after you do it a few times, you don't even need the handout anymore. So amount, almost always an approximation, right? We'll probably be doing approximate amounts. A milliliter is about, on the small test tube, about the height of your pinky fingernail. So that'd be about a milliliter up to there. So you can say about a milliliter, around 2 milliliters, whatever you have. If your drops, 20 drops, something like that, right? If it's a solid, you can do, a marble-sized amount. You can actually weigh it out, those kinds of things, right? Clarity, of course, if it's a solution. Right? Is it clear, translucent, or opaque? We got to look for clarity changes to look for solid formation. Color, of course, we need the colors of our reactants and then our product later to look for color changes. Odor, of course, looking for gas formation. We need the odor of our reactants in our product. Temperature, looking for energy changes. And usually we're to say room temperature or colder or warmer, almost always starting at room temperature unless you specifically heat it up or something. If it's a solution, I need the concentration, right? If I was using that, I would have to say 6 molar. Right? Or something like this, 0.1 molar, because that can change your results. If you use the wrong concentration, you may get something you didn't want or may not get something you should have had. Whoa. And then give me the noun. These are all adjectives. Give me the adjectives and then the noun. Okay? And you can use the chemical formula or the name. I highly recommend the formula because it takes less room and it makes you think more. Hey, now, if your reactant, one of your reactants or more is a solid, we're going to ixnay the concentration. Doesn't make any sense. And we're going to add 2 things. The surface texture. Is it porous? Is it shiny, smooth? Those kinds of things, right? Is it powdery? Those. And add shape. Is it a wire? Is it a foil? Is it a pellet? Is it a small stone? Is it like I said, powders, those kinds of things. So be a little more specific on that. But most commonly, you're using solutions. All right, so that's step 1. Let's look at step 2 and then step 3, and we'll actually do a demo. For step 2, we've already described our reactants. Now let's describe the procedure. What do we do? Most commonly, you'll have reactant A, reactant B, mix them together, shake it, so they were mixed rapidly, right? They were rapidly mixed, done, right? So make sure when you mix them, you don't have just reactant A here and B sitting on top of it. Make sure you shake it up. So you can say, boom, we're rapidly mixed. Mixing implies the shaking, right? So we're rapidly mixed. Well, maybe you heated it over a Bunsen burner. You should probably note that. Or did a specific hot water bath at a specific temperature. Maybe they were added dropwise. Maybe you use this and you did bloop, 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 bloop. We're added dropwise. You see the verbiage there? So be specific. So because the person reading it has to be able to see what you did in their head. And they should be able to make all the proper conclusions without having done the experiment themselves. They could just take your data, see it in their brain, and come up and answer all the questions and conclusions properly. Also record how quickly something happened. Most of the time, you'll mix things, bloop, and it instantly changed. But sometimes it might, bubbled for a minute, those types of things, right? So let's get to the products, and then we'll do the demo. All right, for the products we form, obviously we want clarity, color, odor, and temperature, right? Any evidence of a gas, only if it's visible, like bubbles. And then if your mixture you form is opaque or translucent, if it was clear, we'd call it a solution and we won't look for particles because we wouldn't see them in the first place. But if it's opaque or translucent because of the clarity change, that's an indicator we formed a precipitate, which we probably can't see. So what you do is you, like I said, you shake it up, tilt it to get a thin layer and look into the light and try to see if you can see individual particles or any indicator of any type of precipitate. And then tell me that type of precipitate. I'm going to list those up on the board and show you kind of how to discern one or the other. For the types of precipitate, so again, you take your test tube or whatever, get a little thin layer. Here's what you're looking for. One of these possible 6. Flocculent, gelatinous, curdy, finely divided, crystalline, or colloidal. I give some leeway. Sometimes it's a little more challenging, but this is what I look for. On flocculent, when you're looking at it, you see individual particles and they have a distinct structure to them, like snowflakes or feathers, and has kind of a fluffy appearance to it. Gelatinous, my favorite, typically is translucent. Most of the other ones tend to be opaque. It's like taking a jellyfish and smashing it in there. When you shake it, any particles in there all move and jiggle together. The other ones, if you shake it, the particles move in random directions. But in a gelatinous one, they're stuck in this jelly-like matrix. When you shake it, it goes blah, 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 blah. And sometimes you get slime up on the sides of the test tube. Usually pretty obvious when you have gelatinous. Curdy, real thick and chunky. Finely divided. That's kind of my go-to if I can't figure out what it is. You'll see lots of tiny little particles when you shake it. It's very liquidy, particles moving all over the place, but they don't have a fine structure. They're like dots. Crystalline, right? Think inside like crack a geode open and you see those beautiful crystals in there. That's usually not going to be an option. If you're in lab and you mix A with B and shake it up, you're not going to get a crystalline precipitate in a few seconds. It can take days sometimes or longer, right, to get that fine order with these flat faces. They're really beautiful. We do one in second semester general chemistry here, but it takes like 3 or 4 days to form. So that's not going to be an option, just mixing something real quick, because it takes a long time to form them. Colloidal, you'll never write as an observation because by definition the particles are so small you can't see them. So they look clear to you. So you can mix things together and say, hey, form a clear colorless solution. Well, it might have a colloidal precipitate in it. The only way to really tell is to shine it in light and do what's called a Tyndall test on it. So you would never say you saw a colloidal precipitate in your observations because you can't see one. You could conclude one later. Now, we're not going to have time on this video to do a demo. Let's do that in a second video, and we'll do the example, go through this process, and then we'll talk about different types of abbreviations that are okay for my class, maybe not other classes, but for my class, I think they'd be okay. So here's your details. Let's do the demo in another video.